Unless you have a motion detector, position time graphs can be really hard to understand. So let's take a look and see what happens. This is a detector. It's a motion detector. It tells how close I am to this detector. On your graph on the computer, only pay attention to the top chart. Ignore the bottom chart because it will be very confusing and it's not as accurate. The top chart is a position time graph, which is also called a distance time graph, because your position is what distance you are from the detector. The first thing I want you to do is to notice what happens when I stand in front of the detector and take some data. Here's what happens when I stay still. Here's what happens when I slowly move away from the detector. So you can see when I stood still, the line stayed flat. And when I moved slowly away, the line slowly went up. You'll notice that the x-axis is seconds, and the y-axis is how far away in meters, which are kind of like yards. As I steadily moved away from the detector, my position slowly increased. Therefore, we have a gently sloping line. What about these funny spikes here at the end of the graph? What happened there was I got in and out of the view of the detector. For example, if I collect data again using my hand, watch what happens. Right now, my hand is directly in front of the detector. When I move my hand away, it detects the wall. Hand, wall, hand, wall. So that's what happens when you get out of view of the detector. When I wobble slightly to the side, it doesn't see me, it sees the wall, then it sees me when I get back into its range. So let's watch what happens if I move away more quickly. And look at what happens when I come back. When I moved away quickly, the line was steeper. When I stood still at the end, the line was flat. And when I came back somewhat more slowly, the line is less steep. Notice when it's a positive slope that you're moving away from the detector, and when it's a negative slope, you're moving toward the detector. When you're standing still, it's zero slope because you're not going anywhere. You can't have a straight up and down slope because it's impossible to be here and there at the same time. Let's watch what happens when I start slow and then go fast. See how the graph made a curved slope? This was a slow, faster, 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 faster. It got steeper as I went faster. Therefore, that curved slope shows increasing velocity. A flat slope shows a steady velocity, like when I returned towards the detector. Remember to ignore all the little spikes. So this curved slope here showed me getting faster and faster. This flat slope showed me standing still. And then I reach a steady speed as I came back towards the detector. Let's try another example. What happens if I slowly move away and then stop? Slowly move away and stop. Every time the graph is flat, I'm standing still. Every time the graph is sloped, I'm moving. See how we can make some hills? Every time I moved away, the graph got higher. Every time I moved toward the detector, the graph got lower. Now, pause the video and see if you can answer questions 5 or 6. Then resume the video to see if you get them right. Now you're ready to do the first 4 questions of your lab. In your own words, describe what motion you must do to match each graph below. So tell what motion you must make to get a flat line, a slightly sloping line, a steeply sloping line, and a curved line. Now let's try 5 and 6. In the graph below, sketch the motion of a person walking away down the street, stopping, then walking again in the same direction. Let me do that for you. Number 6. In the graph below, sketch the motion of a person who stands still, walks away, stands still again, then runs back to the starting point.